So I welcome all of you to this webinar, which is focused on the AFSEM instrument, which is an AFM that is built to be integrated into the high vacuum environment of an SEM or a dual beam system. And in the course of the next 40 to 45 minutes, I want to really show you how you can use this tool to do characterization of conductive and magnetic nanostructures by combining the strengths of both worlds of AFM and SEM in a correlative way. But before I start, let me briefly tell you a little bit about the history of our company. So we are located in the beautiful city of Vienna in Austria, and it all started almost 10 years back in 2011 when GTech Microscopy was founded. And from day one, we were really focused on two main topics. One was the development of the AFSEM system, the scanner and stage solution that you will see later on in this webinar. And the second thing was that we also started the development of what we call self-sensing cantilevers. So these are cantilevers that don't need any optical detection to measure the deflection of the cantilevers and are one important part of the whole AFSEM strategy. And you will also learn something about these self-sensing cantilevers in the course of the webinar. It then took us almost 5 years of dedicated R&D work to really finish the AFSEM product, and we made the market introduction of the AFSEM system at the MRS in Boston in November 2016. Then one important thing for GTech Microscopy was that in July 2018, we joined forces with the Quantum Design family, so we are now part of the whole Quantum Design International group, which now, coming from a small startup, really helps us to benefit from the worldwide distribution and service network from quantum design. And up to now, we now have more than 15 installations of the AFSEM systems worldwide, and with the help of quantum design, we hope to grow these numbers substantially in the next years. So we have two main products at GTech Microscopy. One, as I already mentioned, are the self-sensing cantilevers, where we can also offer customized cantilever solutions for customers. But of course, our main product is the AFSEM system that you can see here. So an AFM that is dedicated for high vacuum applications, and due to the intelligent scanner design, it really enables a seamless integration into almost any standard SEM or dual beam system, which then lets you do what we call this interactive correlative analysis, which you will see later on in the webinar in a lot of, I think, very interesting applications. Before I now start to go into more detail in some technical specification of the whole AFSEM system, I want to start with a, I think, very interesting example of correlative microscopy. And in this case, we wanted to answer the question, how can you find the interesting spot on your sample? And I don't know if you can guess what type of sample you're looking at here. This is the bone of a cow. And if you look at this sample, you see that it's a very tall sample. It has an extremely rough surface. And if you give this bone cow to a classical AFM user, he will not be very happy, because it's a very complicated and a sample to do AFM images on such a cow bone structure. But if you now combine the strengths of AFM and SEM, your life gets much easier. Because if you integrate this sample, this cow bone, inside the SEM, you can benefit from the strength of the SEM, that you have this very high lateral resolution, so you can really nicely observe here, what you see here in the SEM image, the surface of the cow bone, and in parallel, you see also here the cantilever from our AFSEM system. So it's very easy and straightforward for the customer to identify the area of interest with the SEM. And in this case, the customer was interested in these small holes here on the surface of the bone that you can see here, which are called lacunae. And when the bone is still alive, these lacunae, there are cells sitting there, which are responsible for the growth and the tensile strength of the bone structure. And using now the SEM, it is quite easy to find these lacuna spots on the surface of the bone structure, and then you can maneuver the cantilever directly to the position of interest on top of this lacuna and take an AFM image of exactly this lacuna area that you see here. And if you now enlarge this image a little bit, you see this beautiful AFM image here where you see all these details on the surface of the bone, all these collagen fibers running back and forth, and this was exactly what the customer was interested in. You can, of course, plot this also in 3D, since it's a real 3D representation in this AFM image. And of course, this is an overview scan. You can also zoom into an area of interest, here where you have all these collagen fibers, take a high-resolution image that you can see here, and then extract a line profile from one of these collagen fibers marked here by this red line. And if you look now at this line profile that you see here below, you can observe this typical ripple-like structure on top of this collagen fiber with this periodicity of around 67 nanometers. If you now look at the scale bar here in Z, which is in nanometers, this also gives you an idea about the noise level that we can achieve with our AFSEM systems. So you see that the height change on this collagen fiber surface is around 2 to 3 nanometers, and we can easily observe this height change even inside the SEM with all the running turbo pumps and all the mechanical vibrations. So the noise level that we can achieve with our system in a standard SEM is around 200 picometers. So we can really get to atomic resolution in Z with the AFM inside an SEM or dual beam system. So now I want to come a little bit more to the technical part and want to tell you a little bit what makes our AFSEM system unique. And I want to do that by starting with what you're probably all familiar with, how a classical AFM works. So in this cartoon, you see the basic working principle of a standard AFM. You have here your cantilever. You use a laser beam that you deflect from the backside of the cantilever, and you detect the deflection of the cantilever with a photodiode. And this setup is for a standalone AFM in air, a rock-solid solution. And it's well designed, and it's a good use for a standalone AFM. But if you now want to start integrating an AFM inside the high vacuum environment of an SEM, life gets more complicated. Because you need this optical readout, which makes an integration into the confined space of an SEM close to impossible. Because the space, especially around the E-gun, is very limited, and integrating an AFM with optical readout is very complicated. This is why we chose a different approach, since we are working with what we call the self-sensing cantilever technology. And for these self-sensing cantilevers, we have a strain sensor integrated into the silicon chip of the cantilever, which can detect the deflection by a strain sensor that is really inside the cantilever. And this makes the whole optical readout obsolete, and therefore enables a seamless integration of our AFSEM system into the highly space-limited environment of an SEM. And to show you the basic working principle, you can look here now at this small video. So we can really, with the core stage, move the AFM scan head directly below the pole piece of the electron gun. We can start the AFM scan, and we can even do that in parallel with the SEM. So you can really have the SEM running and really see what the cantilever is doing on your surface while you're making the AFM inspection. And one benefit of this setup is that the cantilever of the AFSEM system is the lowest point of the whole system. This means that you can really freely move the XY stage of the SEM below the whole AFSEM setup, and therefore have no harm into crashing into the cantilever. And this gives you a room for maneuver to even image very large samples. So every sample that can be integrated into your SEM system, you can also image in combination with the AFSEM system. So now some technical specification for the AFSEM system. There are three main parts for the AFSEM setup. One is the core stage that you can see here in the back of the AFSEM system. It has a travel range in X, Y, and Z of 8, 12, and 24 millimeters, and we can achieve a minimum step size in each three directions of around 50 nanometers. Then, of course, the heart of the system is the scanner itself, It's an XY closed loop scanner with a scan range of 34 micrometers in X and Y, and the scan range in Z is around 5 micrometer. But if you need more scan range in Z, we can also offer a 15 micrometer Z range. The noise level under optimum conditions of the systems in Z is around 70 picometers, and integrated in the SEM it is of course highly dependent on the SEM configuration and the vibration and noise level in your specific SEM or dual beam system. But even for older SEM systems, we always managed a noise level below 0.5 nanometers, which gives you this atomic resolution in Z. And the third part, it's also very important, are the self-sensing cantilevers that we use instead of a classical optical detection of the cantilever deflection. And these self-sensing cantilevers are used to detect the sample topography or other sample properties like conductivity or magnetic properties, as you will see later on in this presentation. The cantilevers, since they have an electrical readout, are all glued and bonded on these small SMD connectors that you can see here. And this gives you the benefit as a user that you don't need to grab this fragile silicon piece with your tweezers, but you can really simply grab the much more robust SMD connector and simply plug it into the scan head, and that's all the calibration that you need to do. So there's no need for any laser alignment. You simply plug in this SMD connector into the scan head, and then you can start right away with the AFM measurements. Here you see an SEM image of how one of these self-sensing cantilevers looks like. You see these strain sensing elements here at the bending edge that enables this electrical detection of the cantilever deflection. I told you in the beginning that we also do a lot of development of these self-sensing cantilevers. And in the last years, we worked pretty hard so that we are able to offer different tip functionalities for our self-sensing element cantilevers. We can, of course, offer the standard silicon tips that you can use for tapping or contact mode to measure topography or mechanical properties. But we can also offer these EBD-grown, high aspect ratio needle-like tips if you, for instance, want to measure in deep trenches. Then we also have a pure diamond tip, which is extremely robust and works extremely well with wear-resistant surfaces. So with hard surfaces, you can even use it for lithography or measure very hard sample surfaces without the harm to damage your tip. And then we can offer more functionalities like a conductive tip for electrical measurements like KPFM, CFM, or EFM. We have magnetic tips for magnetic force microscopy, and as first prototypes, we are also working on thermal tips, which enable you to really do a thermal mapping of your sample inside the high vacuum environment of your SEM. What you see here is with these different cantilever functionalities, we can really offer all standard AFM modes. So now I want to show you a small video because we get the question a lot. How easy can you install the whole AFSEM system inside your SEM or dual beam system? How long does it take? How complicated is it? And I will show you this small video to really demonstrate that you can really do it very fast. So here you can see our demo system in Vienna. And I stopped the video for a second because the important part is here you see these triangles that are screwed to the door of the SEM. This is an FEI Quanta 600 system, and these are the mechanical adapter pieces that we customize for each different SEM or dual beam system. And this is all the mechanical adaptation that we need to do for your SEM system. So these triangle pieces, and we don't need to drill any holes, we use simply screws or holes that are available already on your SEM. And on these two triangle pieces that are pointed out now here, the core stage is attached. And you have only these 4 screws that you see here. And you simply need to put the core stage that you see here on these mechanical adapter pieces. And then you need to fix it to the SEM stage with these 4 screws. And the important part of this integration is that now the AFSEM system is coupled to the Z and to the rotational axis of the SEM stage, but the X and Y movement of the sample stage is still completely independent. And here you can see it now from the top view. And this means if you rotate your SEM sample stage, the AFM scanner will also rotate with the whole setup. And now you have this, what we call a dovetail here. And this is where the AFM scanner is simply slided in on top of the SEM sample now. And you simply have to fix now the scanner with 1 screw. And this is all the mechanical integration that you need to do to integrate the AFSEM system. And once the screw is fixed, all that is left is making the electrical connections. And for that, we need 1 feed through at the SEM. So 1 port needs to be available for our electrical feed through. And then you have simply inside the SEM a high voltage cable for the core stage that is connected now. And then you have 2 connectors for the AFSEM scan head. One is for the low voltage signals, and the other one is for the high voltage signals. So 3 connectors that you need to attach, and this is all the integration that you need to do. And this video is really was in real time without any speeding up, and it takes around 2 to 3 minutes to make this integration. So it's a very fast and easy integration, and it goes both ways. So even if you want to remove the AFM, it simply takes only a few minutes if you don't want to have it integrated all the time inside your SEM system. The benefit of this AFSEM concept is now that it does work for numerous host systems. So we can fit the AFSEM system in a broad variety of standard SEM or FIB models, from TestScan to Zeiss to Geol to FEI Thermo Fisher. But we have also integrated the AFSEM scanner in one of the high-end helium ion microscopes from Zeiss, these Orion nanofabs. We also have a customer who uses the AFSEM system in a UHV chamber. Here you see the setup. This is a wafer inspection tool where one of these modules is the AFSEM, which is used to measure the topography and the roughness of differently processed wafer units inside this UHV environment. And also we have customers who integrate the AFSEM into their lab optical microscopes. So here you see a Keyence microscope where the AFSEM is integrated, and these customers use it sometimes to measure very unconventional samples, like this gear wheel that you see here, which you cannot fit under a conventional AFM, but since we have this optic-free solution, you can really go to the edge of the gear wheel and measure the roughness directly without the need to cut the gear wheel into pieces. And this is really what we call kind of a multi-purpose solution for your lab. So you can use the AFSEM inside your SEM. You can also easily integrate the AFSEM in what we call our AFSEM Air setup that we can also offer. So you can really use it in an acoustic enclosure with an optical microscope as a really standalone AFM. Or you can integrate it into your own optical microscopes in your lab, and you can transfer them freely between different host systems. So that is very easy to transfer the AFSEM system between different host systems and really have a multi-purpose AFM for your lab. Now I want to show you a small video to show you how easy it is to take really a correlative image inside your SEM. And the video will now start. And the first thing that you will see is the infrared camera here inside the SEM on the left, and on the right you see the SEM image. And this highlights now the point. Now we are rotating the sample holder below the AFSEM system, and you can see that we freely can rotate the whole sample holder, and you can have really multiple samples inside the SEM and analyze them with the AFSEM. And now you see the SEM image of a sample here. And this sample is a silicon nitride substrate with holes in it that are covered with freestanding graphene membranes. And now you will see how we can use the coarse stage to move the cantilever into the field of view of the SEM. So here you see now the cantilever. And again, you can move also the sample below the cantilever. So these are two completely independent ways of moving around. Then you can make a fine positioning. In this case, we wanted to really image here at the edge of the silicon nitride holes. And then, as I told you before, you can even tilt the whole setup. So now we are tilting the SEM stage, and the AFSEM scanner is tilting in parallel with the SEM stage. And this then enables you to really get a side view on the cantilever, so you really see the tip of the cantilever, and you really see what the tip of the cantilever is doing while you're doing the AFM scan. So now you see on the left the SEM image, and on the right you see the corresponding AFM data that we are collecting. So we are now measuring, and we are now starting to move over these holes in the silicon nitride substrate that are covered with graphene. And you can really see on the left what the cantilever is doing, and on the right you really see the recording, the live recording of the AFM image. So you have really full control of what you're doing with the AFM inside your SEM system. So now I come to the part where I want to show you different applications to really show you the strength of performing what we call this correlative analysis. And the first example I want to show you is what we call 3D subtractive tomography. In this case, we integrated the AFSEM system in a dual beam system where you also have the ion beam available, so that you can really use the ion beam, in this case a gallium beam, to modify your sample and look at these modifications with the AFM. And the basic experiment we did was using a polymer sample that you see here in blue, and this polymer had some harder beads encapsulated in the soft polymer. And what we did is we started first with an SEM inspection of the sample. Afterwards, we used the AFM to measure not only the topography, but also the mechanical properties, so the elastic modulus of the surface. And then we used the ion beam to slice away part of the polymer sample, and then did this experiment in an iterative way. So do the mechanical measurement with the AFM, use the ion beam to slice away, mechanical measurements, and the ion beam slicing. And in this way, you can really get a 3D reconstruction of the mechanical properties of your sample. And the results you see now here, so we took a series of 8 different images. And what you're seeing here now is not the topography in the AFM images, but really the mechanical properties, so the elastic modulus. And you can use this data to make a 3D reconstruction of this sample, and then make a deconvolution, which beautifully shows you the softer polymer parts and the harder beads that are encapsulated inside this polymer. And this, I think, is a perfect example of where you can combine the strengths of 2 different microscopy techniques, in this case, the ion beam and the AFM, to really get this information that you couldn't get otherwise. Since we don't have an FIB in our demo system, we only have an SEM, we wanted to check how we can use a cantilever tip to modify the surface. And this is what we call the nano plow. Here you see an image of a diamond tip on top of a silicon substrate. And what we tried is, can we use the AFM cantilever with the diamond tip to modify the silicon surface, which is also a quite hard surface. And you now have the benefit that you have this full force control with the cantilever, so you can very precisely define the force interaction between the tip and the substrate. And you will now see in the movie that with a force load of 50 micronewtons, you can really scratch inside the silicon surface, and you can really observe what you're scratching and how you're scratching in real time with the SEM, since you have this high resolution access of seeing what the tip is doing. And I like this video very much because it shows you not only that we can really observe with the SEM what you're doing with the AFM, but it also shows you how wear resistant these diamond tips are. So you can really scratch away the silicon surface without the harm of crashing the tip. And we did this experiment with two different force loads that you see here. So in the lower part with 25 micronewtons, in the upper part with 50 micronewtons. And you can then use the same tip after you did the scratching to make a high resolution AFM scan of these scratches, here for the 50 micronewtons and here for the 25 micronewtons, and get a very good characterization of the scratch geometry that you have created with these diamond tips. As a next experiment, I now want to show you where you can also be much softer to your sample. So not scratch away anything, but really look at the nanomechanical properties, in this case, of 2D materials. The sample that you see here is the same sample that I showed you in the movie, how we can create a correlative image. So it's a silicon nitride substrate with holes, and these holes are covered with 2 or 3 monolayers of freestanding graphene. And the experiment that we now performed was to analyze the mechanical properties of these freestanding graphene membranes. But before I come to the results, I want to show you that there's really more than you typically see in the SEM if you have an AFM integrated. So this is an SEM scan, the highest resolution that we can achieve in our demo system, which is of course not the latest version of the SEMs, but you barely see anything of these 2 or 3 monolayers of graphene that are covering these holes. But if you now come with the AFM and take a correlative image, you can beautifully resolve how the graphene is really covering these silicon nitride holes. So you see some attachment at the edges due to van der Waals forces of the graphene, and in the middle, the graphene is even bended a little bit upwards. And what we now did is, we performed an experiment in dynamic or tapping mode where we worked with a set point of 99%. And for those of you who are familiar with AFM, that means that we only have an amplitude damping of the cantilever oscillation of 1% that we need to get into feedback with the surface. And if you are used to working in AFM with air, there you need to penetrate the water layer that you have on every surface if you're working in ambient conditions. And there you would need set points of something like 40 or 50%, so a lot of amplitude reduction in order to get into feedback with the surface. In high vacuum, you don't have this problem of a water layer, and this means you can work at these extremely high set points, which really limits the interaction force between the tip and your sample. And if you work at this set point of 99%, you can of course take a line scan across this graphene membrane, and what we now did, we decrease the set point, therefore increasing the interaction force between the tip and the freestanding graphene membrane. And you now see the small animation. When we increase the interaction force, you can really bend down the graphene with the cantilever tip. And then if you lower the interaction force, you see a recoverage of the graphene up to the original position. So we can really now use the AFM to characterize nanomechanics of these freestanding graphene membranes inside your SEM system. So now I come to the part which was also highlighted in the topic of this talk. I want to show you some in situ correlative conductive measurements when we are working with a conductive tip. And you see here in this setup that we can also combine the AFSEM scanner with some nanomanipulators. Here you see one of these shuttles of a Klein-Dick nanomanipulator setup. So you can even work with additional add-ons with the AFSEM system, since we have all this space free where the cantilever tip is located. And one thing I want to highlight is that our self-sensing conductive tips are quite unique. Typically, you would use a coated silicon tip for conductive measurements. So you have a silicon tip, you coat it with some conductive material, and this is the basic conductive cantilever. we use a different approach. So we use a very unique 3D nanoprinting technique to create our tips. So this tip is now not coated. This tip is really 3D printed and is made out of pure platinum. And you can see that we can really create 3D structures, and we can add this high aspect ratio platinum tip, which enables us to get to a tip radius of around 10 nanometers. So this gives us what we call this conductive super tips that allows for high resolution conductive imaging. And this work, or this tip, has been created in very close collaboration with Professor Harald Blank from the University of Graz in Austria, who is one of the leading experts in this 3D nanoprinting technique. Now I want to show you some examples. So we use these tips now first for a very simple example. So we measured a gold electrode on a silicon substrate. And on the left part, you see the SEM image. So the bright part is the gold electrode. You have some, what we call a porous transition region due to some etching during the fabrication of the electrode. And this is all on a silicon substrate. Then, of course, you can measure the topography that you see here with the AFM. But if you're working with a conductive tip, at the same time, you get the conductive signal that you can see here on the right part. And there you beautifully can resolve really these porous transition region that you also see in the SEM in the conductive signal. This shows you really that we have an extremely high resolution conductive tip. And in addition, if you now look at the topography, you see here something added on the gold electrode. So something sitting on top of there. And in the conductive signal, this is black. And this immediately tells you that there's some residue, some non-conducting residue on top of your electrode that you can easily resolve in the conductive signal of your AFM scan. This sample is, of course, not the interesting sample of the world, so I want to now show you something that is, from the scientific point of view, much more interesting. This is now a correlative conductive image of a copper graphene Antimon sample. So it's a CVD graphene grown on a copper substrate that is decorated with Antimon particles. And here you can see a correlative image. So this is the SEM image where you see these Antimon triangles, and this is the correlative AFM image. And now I want to show you the conductive and the topography signal from one of these areas. So here you see the topography. And if you now look at the conductivity map, you see that it shows a lot of different conductive regions that can be clearly assigned to different parts of this sample. And I want to show you now this in a little bit higher resolution. So the white parts in this conductive signal now means we have a high current, so a high conductance, and the black part means low conductance. And you can now really see this exposed copper oxides parts with these dark blue parts. You see a graphene flake here, which is bright white because it has the highest conductance. And then you can even see something a little bit less high white, which is probably a multi-layer graphene. And you can also see this grain boundary section here between the two different graphene regions. And you have also some insulating antimony particles, which are black in the conductive signal. So there's a lot of information that you can extract from this correlative conductive image taken inside the SEM. And if you now combine the topography and the conductivity and make this overlay, which is easy with the software, you get this beautiful representation of the AFM topography with the conductivity as an overlay to this data. Now I want to move on to measuring magnetic properties. So here I also want to briefly show you the type of cantilevers that we're using for these magnetic measurements. And this is also a quite unique cantilever since we're using the same 3D nanoprinting technique to create the magnetic tip. But now the tip is not made out of platinum, but out of a magnetic material. In this case, it's iron. So we can 3D nanoprint these high aspect ratio iron tips on top of our silicon tips, which then enables us again to create these magnetic super tips that allow for extremely high resolution magnetic imaging. And as an example, I want to show you some results from a multi-layered magnetic structure. In this case, it's a tantal platinum cobalt platinum mixture that you see here in the SEM, which is not very exciting because it's a flat surface, so you don't see very much. And also the topography in the AFM is not very exciting But if you now look at the MFM signal that you can get in parallel with measuring the topography, you see this beautiful fingerprint-like magnetic structure. So you see really different domains created due to this stacking of different materials, these fingerprint-like magnetic domain structure that you can beautifully resolve with the magnetic tip inside your SEM system. And these samples were provided by Professor Lavacek and Professor Helwig from the University of Dresden, who are now using these samples in combination with the helium beam, and they want to use the helium beam to modify these magnetic domains in their helium microscope, and then use the AFM to see how they modified the magnetic substructure of these samples. I want to show you another example where we measured magnetic properties, in this case for a more industry-based sample, Duplex Steel. And here you can see already in the SEM image different grain boundaries of these steel surface. And if you look a little bit closer in the SEM and turn a little bit on the contrast, you really can see these grain boundaries, where one of these boundaries is a ferromagnetic phase and the other is a paramagnetic phase. And you really need the SEM to exactly locate these grain boundaries. And then again, you can come with the AFM, measure the topography, and in parallel, since we're working with a magnetic cantilever, you get the magnetic response. So this shows you that you can really use the SEM to guide the magnetic cantilever to the area of interest directly at the grain boundary. And then you can really measure the topography, which is a flat surface with some scratches, and you can really see in the magnetic signal two distinct phases, the paramagnetic phase here on top and the paramagnetic phase here below, where you can even observe some subdomains inside the ferromagnetic phase. So now I come to really the last part, where I simply want to show you a few examples where we use the AFSEM system not inside an SEM, but as I mentioned also before in my presentation, you can also use it as a standalone AFM in air. So we can offer really the standalone setup, this AFSEM air setup with an acoustic enclosure, with an easy optics and some mounting part where you can simply use the whole scanner and stage, mount it on the setup, and have a fully functional AFM as a standalone system. And again, here you have the benefit that we don't have any laser optics, that you can work with extremely large or even rough or unconventional samples. And just as a few examples, I showed you this gear wheel already before, where we measured at the edges of a gear wheel. We have customers who work with highly reflective wood coatings and want to measure roughness. We have customers who are working to measure ball bearings. We really measure inside a ball bearing, and you don't want to break or cut this ball bearing. Or we have customers who use the AFSEM for quality inspection of razor blades. This is also a sample that you could not fit under a conventional AFM. With this, I'd like to summarize my talk. I hope I could show you that you can really benefit by combining an SEM and an AFM, which enables you to do this correlative microscopy and measure directly the 3D topography and roughness of your sample without the need to break vacuum. You can also use the AFM to measure mechanical properties and do a stiffness analysis, either by combining with FIB to do this 3D subtractive tomography, or for 2D samples to measure the nanomechanics of graphene. You can add conductivity or magnetic properties and really enhance the results that you can achieve from your sample. And you can do this correlative analysis with an ion beam to measure, again, mechanical, magnetic, or conductive properties also in 3 dimensions. And with this, I thank you for your attention. I hope I could show you that the AFSEM is really a versatile tool